Chapter 10, Crustal Deformation. Deformation is a term that refers to all changes in the original form or size of a rock body. Okay, any sort of compressing the rock, stretching it out, bending the rock is deformation. Most crustal deformation occurs along plate margins. Factors that influence the strength of a rock are its temperature and confining pressure, the rock type, and how much time is it under that temperature and pressure. Folds are when rocks bend into a series of wave shapes. Most folds result from compressional forces which shorten and thicken the crust. There are a couple of types of folds. One is an anticline or upfolded or arched rock layers. They look like they form arches. And synclines or downfolded rock layers. Anticlines and synclines can be symmetrical, so the limbs on either side are mirror images, or asymmetrical, the limbs are not mirror images, or overturned, one limb is tilted beyond vertical. Where folds die out, they are said to be plunging. Okay, so types of folds and strata. So here we have an anticline, and then here we have a syncline. Here we have an anticline and a syncline. This next anticline is an overturned limb because this limb is past 90 degrees. So we have a symmetrical fold. This limb is the same as this limb. This is an asymmetrical fold. This limb is longer than this limb. And here's the overturned fold. So in some rocks, this is what anticlines and synclines look like. Here are nice arched rocks are anticline, and our downward folded rocks of our syncline. When we get to the end of the fold tends to start petering out and it's said to plunge. Okay, so here we have our plunging fold here with our oldest rock is up here in the middle and the plunge is going in this direction. If we did a cross section here and looked at what the rock looked like along this line, it would look like an anticline the top is being eroded off, showing older rocks in the middle and younger rocks towards the outside. Okay. Other types of folds. We have domes, which are circular or slightly elongated circles with their upwarped displacement of rocks, the oldest rocks in a core, or in the core in the center. But when you have a basin, it's also circular or slightly elongated, but the rocks are downwarped or displaced. Downwarp displacement of rocks kind of forms like bowls or basins, where the youngest rocks are in the core. So here is a diagram of the Black Hills of South Dakota, which is a large dome, where you see the older rocks are in the center. The rocks outside, the rocks were upwarped into a dome shape. Here is a basin, the Michigan Basin, where the rocks were downwarped, and the younger rocks are still in the middle. Faults. Faults are fractures or breaks in rocks along which there's displacement that's taken place. Okay, one side has moved relative to the other side. Types of faults. We have dip-slip faults, the movement along the inclination or dip of a fault plate. Parts of a dip-slip fault, we have our hanging walls and our foot walls. Okay, so a hanging wall, the rock above the fault surface is the hanging wall. The rock below the fault surface is the foot wall. So here we have a fault here, and the rocks have been displaced. This layer would line up with this layer. The wall that's above the fault here is your hanging wall, and the rock below is your foot wall. There are several types of dip-slip faults. A normal fault, the hanging wall block moves downwards, like in that photo. This is associated with fault block mountains, and it's prevalent at spreading centers. This is caused by tensional forces. Okay, so here with tensional stress, where these fault blocks are being pulled apart from each other, the hanging wall slips downwards and the foot wall rises upwards. That's a normal fault. These are fault block mountains produced by normal faults. Well, here's one row, and here's probably another row. See, here we have these normal faults. The rock here is being pulled this way and this way, and in between where we have the downward hanging walls, we have our valleys, and then in between we have our ridges. Horst is the name of the mountain, the ridge, and Graben is the name of the valley. So Horst and Graben is also the name of terrain, just like fault block mountains. Okay, There are also reverse and thrust faults. The hanging wall block moves upwards. This is caused by strong compressional forces, so the forces are pushing inwards instead of pulling outwards. The reverse fault, the dips are greater than 45 degrees, but it's a thrust fault when the dip is less than 45 degrees. So here we have compressional forces pushing the blocks together. The hanging wall rises upwards. Since this angle is more than 45 degrees, it's a reverse fault. Now here's compressional forces again. Hanging wall block moves upwards relative to the footwall block, but this angle of the fault is less than 45 degrees, so we call it a thrust fault. We also have strike-slip faults. The dominant displacement is horizontal and parallel to the trend or the strike. Transform fault is one of these. It's a large strike-slip fault that cuts through the lithosphere, often associated with plate boundaries, kind of like the San Andreas fault system. So strike-slip, we have shear stress, where these plates are trying to move past each other in opposite directions. This side wants to move this way, this side wants to move this way. This is a strike-slip fault. Now joints are fractures along where there's no displacement. So these are basic just breaks in rocks. They're not moving. There's no displacement from one side to the other. Most of our formative rocks are in the outermost crust or deformed. Orogenesis is the word that refers to the process that collectively produces a mountain belt. Mountain building at convergent boundaries. Most mountain building occurs at convergent plate boundaries. Okay? The Andean type mountain building, we have ocean continental crust convergence, like the Andes Mountains along South America. Okay, this is relates to the overriding plate with a passive margin, prior formation of a subduction zone. Okay, so our Andes Mountains, are an active margin where these kind of mountains are forming. The passive margins are prior to formation of subduction zone. So like the East Coast North America, we have very passive coastlines. Okay, passive mountain building. The Andean type mountain building is related to that overriding plate again, which is a very active continental margin. Subduction zone forms, deformation process begins, and then you have a continental volcanic arch that forms. A accretionary wedge of material forms. It's what material that's scraped off that subducting plate and pushed against the crust. Examples of inactive Andean type orogenic belts include the Sierra Nevada and the California's coast ranges. Okay, so here we go. We have our subducting plate, materials scraped off and pushed against the continental crust. That's your accretionary wedge. A partial melting, forming our volcanic continental ocean arc. Okay. Continental collisions, where two plates within continental crust converge, i.e. India and Eurasia plate, where the Himalayan mountains and Tibetan plateau are forming. In this case, over time, India approached Eurasia. The subduction was going on here. Once and we have a accretionary wedge starting to form. Okay. Then once the ocean crust was completely subducted, now the Indian crust is starting to merge, push against the Eurasia crust. So we have more fracturing happening and a lot of uplift of the Himalayas and the Tibetan plateau. Okay. Now, convergent boundaries again, continental accretion, the third mechanism of mountain building. Small crustal fragments collide with and accrete to continental margins. The accreted crustal blocks are called terrains. This occurs along the Pacific coast. The small crustal fragments are being pushed against each other, and they start forming mountains. So here we have our oceanic plateaus and fragments. So here, so plateau, we have these oranges are the fragments. They're forming these accretionary wedge mountains. Create terrains along the western margin of North America, along here. Mountain belts, again, buoyancy and the principle of isostasy. Evidence for crustal uplift includes wave-cut platforms. So like on a coastline where you see where the shore is, and you look along the cliff and you see where there used to be a shoreline, or you look a little higher and see where there used to be another shoreline. Those are wave-cut platforms above sea level. So that's evidence of uplift of those rocks being pushed up. So reason for crustal uplift, it's hard to determine, but the concept of isostasy It's a concept of a floating crust in a gravitational balance. When weight is removed from the crust floats higher. Okay, this process is called isostatic adjustment. So here, the heavier parts of the crust are floating, but are deeper in the water. The thinner, lighter blocks are also floating, but they're higher up. They don't extend so far deep. The denser oak wood will sink and float lower, and the lighter, less dense pine will float higher. The continental crust is going to float higher than the oceanic crust. It's isostasy. So erosion and resulting isostatic adjustment of the crust. As material is eroded away, the crust is going to want to uplift. So as these mountains wear down, the crust is going to rise up. Okay, and again, as erosion continues, and eventually we have our continental crust with an old mountain remnant there. End of that chapter.